What if reality isn't what it seems? Close your eyes. Now imagine the ground beneath your feet, the walls around you, even the stars in the sky. None of them are as solid, stable, or separate as you believe. Imagine a world where particles are not things, but possibilities, where time can stretch and bend, where observing something changes its very nature. A world where your conscious awareness, yes, your simple act of noticing, doesn't just perceive reality, but participates in shaping it. This isn't science fiction. This is quantum physics. And it tells us something staggering. Reality, at its core, is not made of stuff. It's made of mystery. Part 1. The nature of reality. According to quantum physics, the classical illusion, a world of things. Before the dawn of the 20th century, physics painted a comforting picture of the universe. It was a grand machine, built of tiny particles and forces governed by laws as rigid as clockwork. Isaac Newton's vision of reality was elegant and absolute, matter in motion, obeying deterministic laws. If you knew the position and momentum of every particle, you could predict the future with perfect certainty. This was the worldview that built the Industrial Revolution and launched rockets to the moon. But it was, in a deep and disturbing sense, an illusion. Because as we peered closer, far closer into the fabric of matter, we didn't find tiny billiard balls or clockwork gears. We found weirdness. What we found was quantum physics. The quantum revolution. When certainty broke down. In the early 1900s, scientists like Max Planck, Niels Bohr, Werner Heisenberg, and Erwin Schrödinger made a series of discoveries that fractured our tidy Newtonian world. At the heart of it all was the quantum, the smallest possible unit of energy. Planck discovered that light, once thought to be a continuous wave, could only be emitted or absorbed in discrete packets. This was the beginning of quantum theory. Then came Einstein's explanation of the photoelectric effect, which showed that light could also behave like a particle. This dual nature, wave and particle, became the first paradox of quantum mechanics. It wasn't just that light could act like a wave or a particle depending on the experiment. It was that it seemed to be both, until you measured it. Reality was no longer fixed. It became fluid, a set of probabilities, not certainties. Wave-particle duality, the first crack in objectivity. The famous double-slit experiment remains one of the most haunting revelations in science. Shoot particles electrons, for instance, through two slits toward a detection screen. If you don't look, the particles behave like waves, interfering with themselves and forming a pattern of bright and dark bands. But if you observe which slit the particle goes through, the interference vanishes, and the pattern becomes one of two bands, as if the particle chose just one path. What changed? You observed it. This is where reality begins to unravel. The act of measuring collapses the wave function, the mathematical representation of all possible states, into a single, definite outcome. In other words, the universe does not commit to a single reality until you observe it. This isn't just philosophical speculation. It's empirical, repeatable, mathematical, and yet it calls into question the very idea of an objective world. Heisenberg's uncertainty principle, limits of knowing. One of the most profound aspects of quantum theory is Heisenberg's uncertainty principle. It states that you cannot know both the position and momentum of a particle with absolute precision. The more accurately you know one, the less accurately you can know the other. This isn't a flaw in our instruments. It's a fundamental property of nature. What this means, philosophically, is that reality resists being pinned down. The more you try to confine it, the more it slips through your fingers. Reality, at its smallest scales, is blurry not because of ignorance, but because of its very nature. This calls into question the foundational assumption of classical physics, that the world exists with definite properties whether we look or not. Quantum mechanics says otherwise. The observer effect, consciousness and collapse. Let's return to the double-slit experiment for a moment. The mere act of observation seems to cause the collapse of the wave function, that is, to select a single reality from a field of possibilities. But what counts as an observer? Is it a human mind? A machine? A photon? This is the core of the measurement problem, and it's one of the deepest mysteries in all of physics. Some interpretations, such as the Copenhagen interpretation, suggest that it is the act of measurement that brings a quantum system into a definite state. Others, like the von Neumann-Wigner interpretation, go further and imply that consciousness itself may play a role in collapsing the wave function. In this view, the universe doesn't exist in any definite way until a conscious observer looks at it. Let that sink in. The world you experience may not be a fixed external reality, but a co-creation shaped by your very awareness. The quantum vacuum, emptiness that isn't empty. At the quantum level, even what we call empty space is seething with activity. Particles and antiparticles blink in and out of existence, borrowing energy from nothing and returning it milliseconds later. This is known as vacuum fluctuation. Space itself is not a void, but a roiling field of potential. This has real consequences. The Casimir effect, for example, demonstrates that quantum fluctuations can produce a measurable force between two uncharged metal plates placed very close together in a vacuum. In other words, even nothingness has energy. Even absence is pregnant with possibility. Reality is not built on solid bricks. It's built on shimmering probabilities. Entanglement, the unity of the whole. Now enter perhaps the strangest and most beautiful aspect of quantum physics. Entanglement. When two particles become entangled, they share a connection so deep that the state of one instantaneously affects the other, no matter how far apart they are. This is not communication faster than light. It's something deeper. It's as if space itself doesn't apply to the entangled pair. They are part of a single system, no matter how distant. Einstein called it spooky action at a distance. But experiments have confirmed it again and again. What does this mean for our understanding of reality? It suggests that separateness is an illusion, that the universe, at its core, is non-local, not made of isolated parts, but of an interconnected whole. This has enormous implications, not only for science, but for our sense of identity. If everything is entangled at some level, then perhaps the boundaries between self and world, observer and observed, are not as firm as we thought. Reality as a probability cloud. In quantum mechanics, nothing is real until it is measured. Instead of saying a particle is here or there, we say it has a probability of being in various places. These probabilities are described by the wave function, a mathematical object that encodes all the possible states of a system. Until an observation is made, the system exists in superposition, a blend of all possibilities. Only when you observe do the probabilities collapse into a definite state. This is the quantum world. Not a world of things, but of potentialities. Not a universe of facts, but of likelihoods. The implications for time and causality. Classically, time flows like a river past, present, future in one direction. But quantum physics complicates this. Certain interpretations, such as the transactional interpretation, suggest that events in the future can affect events in the past. Quantum particles can exchange information in a way that appears to violate causality. This isn't science fiction. It's math. Even more provocatively, quantum retrocausality suggests that present choices could affect the past states of quantum systems. This challenges our understanding of free will, fate, and time itself. Perhaps reality is not a line, but a tapestry one in which all points are subtly connected in a timeless dance. Many worlds, infinite realities, side by side. Another way to interpret quantum weirdness is the many worlds interpretation, first proposed by Hugh Everett. In this view, every quantum event spawns new branches of the universe. Every possible outcome actually occurs in a parallel world. You decide to take a job? In another branch, you didn't. You flipped a coin and got heads? In another, it's tails. This is not metaphor. It's a serious interpretation of quantum theory. According to many worlds, reality is a constantly branching tree, and you are only aware of one sliver. What you call reality maybe just one version among countless others. So, what is reality? This is where philosophy and physics converge. Quantum physics tells us that the real world is not made of solid matter, but of information. That at its core, the universe is not deterministic, but probabilistic. That the act of observation does not simply reveal reality, it creates it. And if reality is created, not discovered, if consciousness plays a role in shaping the world, then we are not passive observers of a fixed universe. We are participants in a mysterious unfolding. Reality is no longer a stage. It's a dance. And we are not merely watching, we are dancing with it. Part 2. The observer effect and the collapse of the wave function. The moment of observation, where possibility becomes reality. Picture this. A particle drifts in a superposition of all possible locations. It exists nowhere and everywhere, not a speck of matter, but a shimmering wave of probabilities. Then, a scientist takes a measurement, and the universe makes a decision. One possibility becomes real. The rest vanish. This is not metaphor. It is the deeply unsettling conclusion of the observer effect in quantum mechanics that the act of observation itself changes the outcome of what's being observed. But more than that, it may be the very mechanism by which reality comes into existence. In a classical world, this would be nonsense. In the quantum world, it is law. So what is this mysterious effect? Why does observation collapse the wave function? And what or who counts as an observer? To answer that, we must go deeper into the heart of reality and face the strange possibility that consciousness might be entangled with the cosmos itself. Wave function, the language of possibility. Before we talk about collapse, we must first understand the thing that collapses. The wave function, often denoted as Q3, psi. In quantum mechanics, the wave function is not just a metaphor or mathematical abstraction. It encodes everything that can be known about a quantum system, the probabilities of where a particle might be, what spin it might have, or what energy state it might occupy. But crucially, it is not deterministic. The wave function gives us a spectrum of potential outcomes, not a definite one. And those outcomes only become actual when an observation occurs. This raises a radical question. If the wave function is all there is before measurement, and the wave function is only a cloud of possibility, then what exactly is the universe before we look at it? The honest answer is, we don't know. Schrödinger's cat. A thought experiment in paradox. To illuminate the absurdity and truth of quantum collapse, Erwin Schrödinger proposed a now famous thought experiment. Place a cat in a sealed box with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the counter triggers. The poison is released, and the cat dies. If the atom does not decay, the cat lives. Quantum mechanics tells us that until we open the box, the atom exists in a superposition of decayed and not decayed states, and thus, the cat is both dead and alive. Only when you observe do you find the cat either alive or dead. This bizarre scenario isn't just a mental exercise, it points directly to the problem of measurement in quantum theory. If the quantum world is truly in a state of superposition until measured, and if measurement causes collapse, then when exactly does the collapse happen? When a Geiger counter clicks? When the cat dies? When a human opens the box? Or only when someone becomes aware of the result? This is the observer effect in its most provocative form, a universe that does not resolve itself into reality until we participate in it. The role of the observer. What does it mean to measure? In classical science, the observer is irrelevant, just a neutral bystander gathering data from an objective world. Quantum physics destroys that assumption. In quantum experiments, the observer plays an active role. The choice of what to measure and whether or not to measure at all changes the outcome. But who or what qualifies as an observer? This remains one of the most hotly debated topics in the foundations of physics. There are three main schools of thought. Instrumentalist view. Measurement occurs whenever a macroscopic system interacts with a quantum one, say, a detector clicks or a pointer moves. Consciousness is not required. Consciousness causes collapse view. Observation isn't complete until a conscious observer becomes aware of the outcome. The universe doesn't decide until a mind is involved. Many worlds view. There is no collapse. Every possible outcome happens in a branching multiverse. Observation merely determines which version of the observer continues in which branch. Each interpretation carries radical philosophical implications. Von Neumann and the chain of observation. Hungarian-American physicist John von Neumann offered one of the most mathematically rigorous treatments of the measurement problem in his 1932 work Mathematical Foundations of Quantum Mechanics. He noted that in a quantum measurement, we can always push the boundary of what's being measured further back. A particle hits a detector. The detector changes state. A neuron fires in the observer's brain. The observer becomes aware of the outcome. At what point in this chain does the wave function collapse? Von Neumann argued that no physical system, not even the brain, forces the collapse. Only conscious awareness does. This led to the controversial idea that consciousness is not outside the quantum system, but a fundamental part of it. If true, this would mean that consciousness does not emerge from the physical world, but rather, the physical world emerges from consciousness. Wigner's friend. The observer's observer. To further explore the observer effect, Eugene Wigner proposed a disturbing variation of Schrödinger's cat. Imagine your friend performs the cat experiment in a sealed room. From their perspective, once they observe the result, the wave function collapses. But from your perspective, standing outside the room, your friend and the cat are still in a superposition. So whose reality is real? Wigner's thought experiment reveals the relativism of quantum collapse, that different observers may experience different realities. This directly challenges the idea of an objective universe shared by all. It hints at a deeper truth. Perhaps reality is not a singular thing, but a set of observer-dependent constructions. Consciousness as a quantum phenomenon? Many scientists and philosophers have speculated that consciousness itself may be a quantum process. Not just a biological byproduct of brain chemistry, but a non-local probabilistic phenomenon akin to wave function behavior. Notably, physicist Roger Penrose and anesthesiologist Stuart Hameroff proposed the ORCHO, orchestrated objective reduction theory. They suggest that microtubules, tiny structures in brain neurons, may host quantum states that collapse in a coordinated way, giving rise to conscious experience. While this remains speculative and controversial, it reflects a growing intuition that consciousness and quantum mechanics are not separate domains, but intertwined. If consciousness and observation are deeply linked, it redefines our role in the cosmos. Delayed choice experiments. The future shapes the past. To truly grasp the strangeness of the observer effect, consider John Wheeler's delayed choice experiment. Imagine the classic double-slit setup. A photon is emitted and travels toward two slits. Now imagine you wait until after it has passed the slits to decide whether to observe which path it took. Incredibly, your choice in the present appears to retroactively determine what the photon did in the past. If you measure the path, it behaved like a particle. If you don't, it behaved like a wave. Your future decision rewrites its history. Experiments have confirmed this. Reality is not a fixed timeline. It is a looping feedback between potential and perception. Quantum eraser experiments, erasing reality itself. Even more mind-bending are quantum eraser experiments, where information about a particle's path is erased after the fact, and the interference pattern, or lack thereof, changes accordingly. This suggests that knowing or not knowing something affects what is real, not just in theory, but in actual measurable outcomes. In other words, what you know or could have known changes what happened. Reality is not passive. It is participatory. It doesn't unfold like a script. It waits for you to choose your role. The participatory universe. Wheeler's final vision. The physicist John Wheeler one of the pioneers of quantum theory, eventually came to a radical conclusion. The universe is not a static backdrop upon which events unfold. It is a participatory process, in which observers bring forth reality through acts of measurement. He called this the participatory anthropic principle, the idea that consciousness is not merely in the universe, but essential to its existence. Wheeler imagined a universe in which the past, present, and future are co-created through a vast web of interactions, where each act of observation weaves a thread in the cosmic tapestry. In his words, no elementary phenomenon is a phenomenon until it is an observed phenomenon. From physics to metaphysics. What does it all mean? Let's pause here. We've come a long way from wave functions to Schrödinger's cat, from von Neumann's consciousness collapse to Wheeler's participatory universe. What are we left with? We are left with a view of reality that is deeply strange and deeply personal. A view in which the world does not exist in definite form until we look. Conscious awareness may be involved in shaping what is real. The past is not immutable. The future is not fixed. Observation is not passive, but participatory. Reality, at its core, is not a set of things, but a relationship between knower and known. This is not mysticism. It is physics. Yet it flirts with philosophy, psychology, even spirituality. The observer effect is not just about particles and detectors. It is about you. It is about the possibility that every act of perception is a creative act, that every moment of awareness shapes the cosmos. Not because you wish it, but because you observe it. Conclusion: you are not outside the universe, you are inside the equation. In classical science, you are a detached observer. In quantum science, you are part of the equation. You do not merely look at reality, you co-create it. Every time you open your eyes, measure, perceive, you participate in a cosmic unfolding. Reality is not a solid structure. It is a field of infinite potential awaiting your participation. And that's the most profound shift of all. We are not discovering a universe out there. We are awakening to a universe within and between. A universe that sees us seeing it. Part 3. Entanglement and non-local reality. The cosmic web. A universe of threads, not things. Imagine two particles, born from the same event, like twins separated at birth. One is sent to one end of the universe, the other to the opposite side. They could be galaxies apart. Now, measure the spin of one particle. Instantly, and I mean instantly, the other particle's spin resolves in perfect correlation. No signal passed between them. No information traveled the distance. Einstein called this spooky action at a distance. We call it quantum entanglement, and it challenges every notion of space, time, and causality we've inherited from classical physics. Because in the quantum world, separation is an illusion. Entangled particles act as a single system no matter how far apart they are. This is not science fiction. It has been tested, verified, and accepted as fact. The implications? Nothing short of revolutionary. Let's explore what this means not just for physics, but for your life. What is entanglement, really? At the quantum level, particles can become entangled through interaction. This means their physical properties like spin, polarization, or momentum are correlated in such a way that measuring one immediately affects the state of the other, regardless of the distance between them. But the key here is that these particles do not have independent states until measured. Instead, they are described by a joint wave function. This wave function doesn't say, particle A is this, and particle B is that. It says, together, they are this whole pattern of probabilities. Only when one is measured does the entire system collapse into definite outcomes. This is not just mathematical elegance. It is experimental fact. The EPR paradox and Einstein's discomfort. In 1935, Einstein, along with Boris Podolsky and Nathan Rosen, published a paper challenging the completeness of quantum mechanics, now famously known as the EPR paradox. They argued that if entangled particles could affect each other instantly over large distances, then Either quantum mechanics is incomplete and missing hidden variables that determine outcomes in advance, or reality allows for faster-than-light communication which violates relativity. Einstein couldn't accept either conclusion. He famously said, "God does not play dice with the universe." But decades later, physicist John Bell developed a theorem that showed, if quantum mechanics is correct, then local hidden variables cannot explain the observed results. And when Bell's theorem was tested first by Alain Aspect in the 1980s and later by many others, the results were clear. Quantum entanglement is real, and it is non-local. Bell's theorem. No room for classical thinking. Bell's theorem proves that no theory based on local realism can reproduce the predictions of quantum mechanics. Local means no influence can travel faster than light. Realism means physical properties exist whether or not they're observed. But entanglement violates one or both. Either reality is non-local or it isn't real in the way we think. This is the point where philosophy must join hands with physics. Because if two entangled particles act as one system, even across space, then the universe may be fundamentally interconnected in ways that defy our senses. Quantum wholeness. Bohm's deeper order. Enter physicist David Bohm, a brilliant mind often at odds with mainstream thinking. He proposed that the quantum world reveals a hollow movement, a deeper order beneath space and time. In Bohm's view, the universe is like a hologram. Each part contains the whole. Entanglement is not a signal traveling across space. It is the expression of an undivided wholeness. What looks like separation is just a projection. You are not separate from the world. You are in the world as a ripple in a greater ocean of being. As Bohm wrote, the notion that all these fragments are separately existent is evidently an illusion, and this illusion cannot do other than lead to endless conflict and confusion. Entanglement and time. The future entangled with the past. We've seen how entangled particles influence each other across space. But what about across time? Recent experiments show signs that particles can become entangled even when created at different times, one in the present, one in the future. This temporal entanglement suggests that time itself may not be linear. Instead, past, present, and future may be entangled together, forming a web of relationships rather than a line of causes and effects. This mirrors ancient philosophical ideas that time is not a river but a tapestry. Quantum physics may be bringing those intuitions into the realm of science. Quantum biology. Entanglement in life. Entanglement isn't just for particles in a lab. It may be at work inside you right now. Emerging research in quantum biology suggests that birds navigate using entangled electrons in their eyes. Plants may use quantum coherence to transfer energy during photosynthesis. Even human brain activity may display entanglement-like correlations between regions. If true, this means entanglement isn't confined to physics textbooks. It's woven into life itself, perhaps even into consciousness. You are entangled with the universe. Pause. Think about what this means for you. If entanglement is real, and it is then, you are not an isolated self moving through a cold, mechanical world. You are part of a grand, interconnected whole. Your thoughts, your choices, your attention, they ripple outward in ways we do not fully understand. The boundary between you and everything else is blurrier than it appears. Maybe this is why people sense that meditation, intention, prayer, or focused emotion have effects beyond the body. Maybe there is a physics beneath the mysticism, not supernatural, but supernatural. Maybe entanglement is the science of connection we've always intuited but never explained. A new picture of reality. From separation to relationship. Einstein's universe was elegant but impersonal, a realm of particles and forces moving predictably through spacetime. The quantum universe is messier but more human. It's a realm of possibility, observation, and relationship. Entanglement tells us that reality is not made of objects, but interactions. Not of things, but of relationships. And if that's true, then maybe love, empathy, attention, the invisible threads that bind us, are not secondary to reality. Maybe they are its source code. Conclusion. Storyteller style. The invisible threads that weave the cosmos. Let me tell you a story. Not one of kings and battles or machines and markets, but a story of threads. Imagine the universe not as a machine, but as a vast living tapestry, woven not of matter, but of meaning. Every particle is a thread. Every wave is a possibility. Every observation is a knot tying past and future, self and other, here and there. In this tapestry, nothing is truly separate. The flicker of an eye in one galaxy may echo in the spin of a particle in another. You are not outside this tapestry. You are a pattern within it, a movement, a rhythm, a song sung by the whole, through you. And entanglement? It is the whisper of the universe reminding you that you are never alone. It is science and it is soul. It is the logic of light and the language of love, spoken in the grammar of quanta. So the next time you close your eyes and feel connected to another person, to the stars, to something larger, don't dismiss it. You may be feeling the truth the universe has been humming all along. We are entangled. We always were.